Hello everyone, I'm Lipfert. I realize I'm the last thing between you and a very well-deserved coffee break, so I try to be brief and entertaining. But of course I would like to first thank the organizers for putting together a really wonderful meeting, and of course for inviting me and giving me the opportunity to speak. So I would like to take this back to the level of single molecules, at least for the most part. And here's a very brief outline. I'll tell you about magnetic tweezers in case you don't know what they are. I'll tell you about some modern or novel ways to use magnetic tweezers to directly measure torque and twist. And then I'll basically talk about two applications. One is to double-stranded RNA, and then very briefly to Rad51 filaments and nucleosomes, so essentially to protein-nucleic acid interactions. As you probably all know, single molecule methods have been developed to manipulate individual macromolecules, and they have taught us a great deal of things, and sort of the workhorse techniques are optical tweezers and atomic force microscopy. While these methods are very powerful, they both, or all of them, intrinsically operate in this space with linear extension and linear force. Okay, so you pull and you in a certain direction, and you measure the extension or deflection. However, in biology, not just forces and extensions, but also torques and rotation can be very important. Chris Judzinski this morning mentioned the F1 F0 ATPase, which is a rotary motor. Another classic example is the bacterioflagella motor, which will make a short appearance in my talk. And then a place where I'm sort of particularly interested in, where this rotational motion also plays an important role, and where we already heard several talks about, is to the double helical nature of DNA. The DNA is a double helix. If you want to transcribe it or replicate it, you have to open it up, and like the case in these sort of old-fashioned telephone cords, this will create tangles, namely more specifically positive supercords ahead and negative supercords behind the sort of very schematically shown here replication or transcription machinery. And in the cell, these supercoils are really sort of a feature of cellular life, and there are mechanisms such as topoisomerases and gyrases to deal with these sort of topological constraints. Now, if you want to study these rotational motions at the single molecule level, magnetic tweezers are a very powerful tool. And here's sort of a very brief introduction. In magnetic tweezers, you typically have some molecule of interest, shown here in blue, attached to a surface with one end into a small magnetic bead. With the other end, you have magnets. The first thing you can do, you can move your magnets up and down, and that will control the force. But in addition to this, you can rotate your magnets, and you can basically start to twist your DNA molecule, in this case, for instance. And here's sort of the classical curve that we record in the magnetic tweezers. The different colors are different forces. They correspond to a specific height of the magnet. And then basically, it's not my power cord, so I apologize, but I'll torture this power cord a little bit. So the experiment that you can do, you can twist it. And then you will form these extra coils here. And they're called plectonyms if they're made from DNA. And this gives rise to this behavior that you have this buckling regime here, where basically every extra turn just makes an extra plectonym. If you do this at low forces, you can have positive or negative plectonyms or supercoils. If you do this at what we call high forces, which are actually still very low, above 1 piconewton, these curves become asymmetric, and here the double helical nature of the DNA shows its effect. Namely, you can still have these supercoils when you overwind, but if you unwind, you typically melt the DNA and the base pairs break. Now, melting here means the base is separated. This is not thermally induced, but this is mechanically induced by negative torque. A few more words about sort of what we like to call conventional magnetic tweezers. One is, what are the typical forces? And there it turns out that if you want very large forces in the nanonewton range, you're best suited with an AFM. Optical tweezers can go down towards, in the, say, 1 piconewton range. But if you want to look at very low forces, be it for these sort of supercoiling phenomena, be it for something else, you're very well off using magnetic tweezers because you can go very low. And one thing that I also want to just very briefly mention is you can understand the forces in magnetic tweezers by simply considering the external magnetic field, considering the induced magnetization in the beads, and then, as we physicists always like to do, take the negative gradient of this energy, and that gives you the force, and this works out quantitatively. And here you basically treat the bead simply as a paramagnet that you learned in first year physics. What's a little strange is, how come you can rotate the bead because if you take your textbook paramagnet, the paramagnet doesn't care which way it's magnetized, so you would rotate your magnets, as I've told you, you would rotate the field, but the bead wouldn't rotate, only the induced magnetization would rotate. So clearly there must be some sort of anisotropy, and something I would almost call the sort of inverse of the normal flow of biophysics. We actually use biology now as a tool to study physics. We carried out the following experiment. We stuck E. coli cells to a glass slide, and it was a mutated strand that would only rotate in one direction, and that doesn't have the full flagellum, but only the first bit called the hook. And we attached these small paramagnetic beads to the hook, and then have our magnets on top. And we use this essentially to just generate a torque. And what we can then do, we can bring down the magnets until the motor almost stalls. And we use this basically to probe the properties of these beads in sort of under torque and rotation. And I'm just showing you one particular experiment where we go to a point where we almost stall out the motor, and you wouldn't see, and then the different colors correspond to different settings of the magnet, same height, but different rotation. What you see is you see always two preferred positions. Okay, so you see a green, here, blue here that are separated basically by half a turn. From this we concluded that the potential that the bead sees must be pi periodic, and that immediately tells you there is not a ferromagnetic component, which was actually proposed in the literature, but there must be something else, and we basically find support for a soft axis model. And I'm just mentioning it briefly here. We did some more sophisticated modeling, really quantitatively test models. But I think we have some angle now on this anisotropy or symmetry in the magnetization that allows you to rotate. One last aspect that I would like to briefly mention about sort of conventional magnetic tweezers, we now have an increasing ability to multiplex these measurements. It's a camera-based technique. We image the bead using a CCD camera. And since CCD cameras are getting better and better, basically because we all carry one around with us all the time, we can now actually measure dozens to hundreds of beads at the same time. Each of these is attached with a single molecule, so you can basically perform many single molecules in parallel. Now going back to the scheme that I already showed you, I try to argue magnetic tweezers are a great tool to apply forces and torques, but to be honest, these conventional magnetic tweezers, they don't actually directly measure the torque. What I told you, we can coil, we can look at the results of the coiling, but we don't actually measure the torque. Now to overcome that shortcoming, we developed new magnetic tweezers that we call magnetic torque tweezers, where we made basically two fairly straightforward changes to the sort of standard setup. The one involves an ability to, in addition to track the XYZ position of the beads from camera images, also track the angle. One way to do this, which is sort of the conceptually easier one, is to basically just perturb the spherical symmetry by adding some non-magnetic particles. Then you have sort of here an asymmetry in the image, and you can teach a tracker track rotation. Another thing we had to do to make the torque measurement work was to change the geometry of the magnet to alter the properties of the magnetic field. Now let me tell you how that constitutes a torque measurement. Imagine you can track the rotation angle of your molecule as a function of time. When I say rotation angle, I always mean the rotation angle around the z-axis, or the axis of the molecule, if you like, the tether axis. If you track the angle as a function of time, you will find a Gaussian distribution which has a mean that corresponds to the equilibrium position of this angular trap setup by the magnet. And you have a standard deviation of the fluctuation, and that's sort of a standard trick in single molecule physics. You can use the width of the fluctuation to calibrate your trap stiffness. It's just the thermal energy divided by the variance of the fluctuations. Now, if you start with a torsionally relaxed molecule, and now you wind it by some integer number of turns n, the molecule, if it has torsional stiffness, like double-stranded DNA or double-stranded RNA, doesn't like to be twisted and will actually push back. And then you can basically, you again record angular fluctuations, get another distribution, the distribution is shifted, and your torque measurement is simply taking this shift in the angular position, multiply it by this pre-calibrated rotational trap stiffness, and this directly gives you the torque. This is essentially Hooke's law, just instead of linear extension and force for rotational sort of shift and torque. Another scheme that is related, that looks very similar but is missing this little side magnet, is a scheme that we call 3D orbiting magnetic tweezers, where we perfectly align the magnet so that the field is vertical here. Now actually the angular position of this particle isn't constrained by the magnets anymore and can rotate freely, and so what happens is it basically gets pulled up, rotates around like this, If you track its xy position as a function of time, it looks very funny. If you track x versus y, you see that the fluctuations lie on this donut. You can understand this pattern from this geometry where you pull up the bead and the bead rotates. And then it turns out that essentially from the position of the donut, remembering some high school geometry, you can actually deduce the rotation angle without having to use this fiducial marker trick. Okay? And so basically, well, we did a control where we had one of these fiducial markers on the bead. We tracked the fiducial marker, we tracked the angle between xy. The two things perfectly correlate, and then you get a correlation coefficient of 0.99999, which is probably the highest correlation coefficient I've ever seen in a biophysics measurement. And so essentially, as a friend of mine would say, you can track angle without having to track angle. Now, having these tools in hand, we started to tackle some what we thought interesting applications. And the first story that I would like to tell you is about comparing double-stranded DNA, which had been already measured in a number of single molecule measurements, to double-stranded RNA. Now, both form a right-handed helix. DNA forms a B-type helix. RNA forms an A-form helix. They have some differences. The A helix is a little bit thicker, and it has a little shorter rise per base pair. There's also a difference in sort of the pattern of the grooves. The difference between major and minor grooves is somewhat less pronounced in the A helix. Now, to understand the mechanical properties of these things, the question is, how much detail do you need? Do you need really the detail of every single base or every single atom? Or perhaps can you get away with a more coarse-grained representation? And essentially, the sort of standard model of long double-stranded DNA is this model essentially also known as a Kirchhoff rod, namely an isotropic elastic rod, which is a very much of a simplification. Now, that isotropic elastic rod has essentially three ways to the form. It can bend, it can stretch, it can twist. And then essentially there are elastic constants associated with each of these deformations. The energy of the rod is an integral over the contour. And then there are four terms here, and no worries, we don't really need the details. But note there's four elastical constants called A, B, C, and D, and I'm following here Nelson's notation. And A is the bending persistence length, so that's the term related to bending. B is the stretch term, D is the stretch modulus. C is the twist modulus, or twist rigidity. And then finally, there's one cross term, the so-called twist-stretch coupling, or D. Okay? So the next few minutes of my talk will be very simple. It will follow A, B, C, and D. Okay, so briefly, that had been done before. A, the bending persistence length, you can get from a simple force extension measurement, where we vary the force and observe the extension. And if you do this at low forces, this is very well described by the worm-like chain model of entropic stretching elasticity. And from this worm-like chain model that you can fit to the data, you can determine the bending persistence length A and actually also the contour length. And what we find is that the bending persistence length for RNA is on the order of 55, 60 nanometers, and for DNA is 45, 50 nanometers. So they're very similar, but RNA is about 20% more stiff when it comes to bending, and both of these quantities actually depend on salt concentration. Now, to get the stretch modulus, we perform a quite similar experiment, but just go to simply higher forces. And what you see is if you go above something like 10 piconewton, there start to be systematic deviation from this inextensible worm-like chain model that we used in the previous slide. And, but you can still fit a model that looks kind of similar, which is the extensible worm-like chain model, where you simply include the fact that there can also be enthalpic stretching, namely the stretch modulus B, or to confuse you, I like to actually change notation and use B times KT, which is S, which is the more convenient way to write it, because S has units of force. And what we find is that the stretch modulus for RNA is about a third or so of that of DNA, namely about 350 piconewton, as opposed to 1,000 piconewton for DNA. But note, that roughly sets the scale where that sort of stretching deformation becomes important, and note that they are still very large compared to the typical forces that we have, so even though RNA is easier to stretch, it is still pretty stiff. So now we come to the part where the magnetic tweezers really shine, namely C, the torsional persistence, and so we carry out the following measurement. And that is essentially now the DNA version of the data or the similar measurement that I showed you earlier on, namely where we look at the molecule extension as a function of turns, and having these torque measuring magnetic tweezers at the same time, you can now also measure torque versus turns. Okay, again, the different colors are different forces, and what you see is Let me walk you through it here. There's a regime close to 0 turns, where the extension almost doesn't change, and where the torque depends linear on the number of turns. So that's the regime where a DNA molecule essentially behaves like a rubber band in the twist degree of freedom. And from that slope, you can actually determine the torsional persistence thing, so the torsional stiffness. Then there's a regime where you go beyond the Buckley point, where you get a linear decrease in extension as the increasing number of turns, and where the torque actually goes into a plateau. This is sort of past the buckling transition, and from the value of this plateau, you can determine what's called the buckling torque, so the critical torque for buckling. Again, you can go negative, and if you're at high enough forces, you will sort of melt the molecule. Double-stranded RNA, like obviously double-stranded DNA, can melt, and you can measure the melting torque from this plateau. And finally, there are actually some additional transitions, and one I'm going to mention very briefly is if you're at forces above about 5 to 6 pg, you do not get buckling anymore, and you overwind, and you get actually new conformation, the term pRNA, in analogy to pDNA that had been seen earlier in the hypothesis is that that's actually a conformation where the bases are flipped to the outside, and the P stands for Pauling. Basically, that was this incorrect assumption by Linus Pauling initially, how the DNA, so under normal conditions, would look like. Well, so he was wrong in that regard, but it turns out he's sort of right. If you pull on it, if you overwind it, you can get that sort of conformation. Okay, here's a sort of quantification of these slopes in this linear torque versus turn regime. You get the effective torsional stiffness, which turns out to depend on force. So two things here. DNA and RNA are very similar. RNA is red, DNA is blue. There's a model from Roy Nelson, which sort of describes the trend, but doesn't quantitatively fit the data. There's some really interesting thoughts why that is. You can ask me over coffee, but in the interest of time, I'll go on and just sort of finish this part by saying we've now mapped out the complete phase diagram of double-stranded RNA and also done some controls for DNA, which is most of you know. And overall, everything I've told you so far, double-stranded RNA is actually pretty similar to double-stranded DNA. The parameters vary by 10, 20, 30%, but they're quantitative, at least qualitatively very similar. Now, I'd like to go on and describe two really interesting differences that we found. And one involves the so-called twist-stretch coupling parameter, this last elastic parameter called D. Now, as a quick introduction, what is the twist-stretch? All these other elastical constants have to be positive, right? A negative bending persistence would be you get energy if you bend your thing. That would be very strange. Maybe sort of nanomaterial, but that would sort of be very unusual. Turns out this coupling term can be positive and negative. Could be negative, that would mean there's no coupling. It could be positive, and what that means is if you overwind the helix, so you wind it more in the direction of the helix, the polymer will shorten. It could also be the opposite. It could also have a negative twist-stretch coupling, would mean if you overwind the helix, it lengthens. Now the macroscopic intuition, if you go back to your room, you take your bathroom towel, you wind it up into a helix, and now you wind it a little more, you would usually expect it to shorten. At least, well, I encourage you to try. And so that was the naive expectation. Now, we did these measurements, and for DNA, this was actually already done before. And it had been known DNA is blue, that DNA actually does not behave like your bathroom towel, but that DNA actually lengthens if you overwind it, and overwinding gives positive turns in this object. And of course, that was a big surprise, and that came out in 2006. And then we expected, though, to RNA to be like DNA, but it turns out RNA is actually like your bathroom towel. So RNA is actually like the macroscopic intuition, but strangely enough, unlike DNA. So that was a big surprise. Well, we did some more quantification. We quantified the slopes. Our DNA measurements are very good agreement with previous DNA measurements. For RNA, we looked at the force dependence. There doesn't seem to be a systematic force dependence over the range we look. And so the summary is, very strangely, RNA shortens when overbound, and DNA lengthens when overbound. And it's sort of twist-stretch coupling is not as design. Now, given this surprising finding, we were, of course, immediately wondering, how can we explain this? Now, here is a chart, basically. The experimental result that I've just shown you is that if you overwind DNA lengths in RNA short. Now, I had a really easy time finding a model that would explain that behavior, because initially it was thought that DNA behaves like a bathroom towel, and people published papers and made models that essentially were sort of an isotropic elastic material with some density. Sorry, not isotropic chemical, but otherwise isotropic. And the problem was, that basically predicts this thing to short, and that's correct for RNA, but that turned out to be incorrect for DNA if you do high-resolution measurements. Then when these high-resolution measurements came online, that showed that DNA in fact lengthens when you overwind it, people made a new class of models that all involve sort of a stiff backbone wrapped around the core, and they get the DNA behavior correct. But the problem is if you plug in parameters of, say, helicity for RNA, actually they expect RNA to be like DNA, and that is inconsistent as the experiment. Then I went out and got two colleagues of mine, Ritu Das, from Shao at Stanford to run a big computer simulation, or actually not that big computer simulation, but to simulate DNA at the level of a base pair, so where you basically feed every base pair is one object. And we actually managed to reproduce a lot of the things that I just told you from this computational model, but we failed miserable when it came to the twist stretch, because basically the model predicted essentially RNA and DNA would be the same in two lengths. It turns out just very recently, the group at Oxford came out with a paper called OxRNA, this is Christian Matek et al. And they have a model where it's a little more fine-grained, but still very coarse-grained. They have, I think, 2 sort of dummy atoms per base. And their model gets RNA correctly, but then unfortunately incorrectly gets DNA to be like RNA, so they too fail. And I have good news for you. Together with the group of my colleague Martin Sararias in Munich, well, they really ran long, all-atom, explicit solvent MD simulations and analyzed the fluctuations. And here's some snapshots from these simulations. And it seems like if you do all-atom MD, there's good news. They seem to actually get that different behavior correctly. So here's this nice button. So here's the twist, and here's the rise. And this basically shows you that RNA gets longer, DNA gets shorter. And from these simulations, we also have some insight now why that is. It depends essentially how the grooves that form when you're twisting. And so that seems to be the story here, that you might actually, for some cases, really need all that, I suppose. Okay, finally, one other surprising difference. We looked at dynamics. We did a measurement where we basically, again, twist our molecule and then hold the magnet still, both the up, down, and the rotation. And you can then be in a situation where you basically jump, just thermally activated, between a twisted and straight state and a just buckled and somewhat a twisted state. And here's real data. This happens for both DNA and RNA, and the really critical point in this plot here is the time scale. So under otherwise identical conditions, we found RNA will hop a few times every 100 seconds, and under the same conditions, a DNA molecule hopped a few times every second, which really means the dynamics of this hopping transition, so that the transition between the pre-buckled and the post-buckled state, is about 2 orders of magnitude faster for DNA than for RNA. Now, we did many of these traces and some of the more sort of sophisticated analysis, but I just give you this sort of upshot here. We characterize the buckling time, which is basically at the 50-50 point, your rate going up is the same as the rate going down. And that rate is, the events are the Poisson process that we showed, and basically they're exponential distributed. And there's one characteristic time scale. Now that characteristic time scale we call the buckling time. It's plotted here for RNA as a function of force and salt. And in that measurement for DNA, basically our camera was too fast to reliably, too slow to reliably resolve these fast events. So we basically got sort of an upper limit, and basically you have to compare this point to this point here, and basically this order is different. For RNA, we analyzed the data, and we found that there's a roughly exponential dependence of this characteristic buckling time and force, and from the fit you get the distance to the transition state, which is a little tricky here because there's really this rotational and looping involved, but all we can do here is fit to this one length scale. We found it to be something like 5 nanometer. Now, my student Philip and my postdoc Willem have set up a really high-speed camera now where we can track a kilohertz and beyond. And that allowed us to get more data on DNA, where we can now actually start to resolve these very fast events. This is basically a replot of the same data from the previous slide. This is now new data for DNA. And again, you see actually force and salt dependence. It seems like the transition state is a little bit different. And so what that must mean, and to take one more step back, basically I initially told you a lot of properties of DNA and RNA are actually very similar. So that makes this very different rate even more surprising, because the equilibrium properties of this pre and post-Wachtel state are basically the same to within 30%. Now, of course, if the rate is so different, that basically must mean the transition state barrier is lower for DNA than for RNA. And my speculation, that's at this stage really a speculation, is that perhaps if the transition state involves fairly sharp bending, and certainly these fits showing distances to the transition state of a few nanometers would indicate that the length scale is indeed on the scale of a few nanometers. Now, there's a number of experiments, including from T.J. Haslett recently and many others, that perhaps DNA is much more bendable on very short scales than this one-leg chain standard isotropic backbone would predict. And so perhaps that sort of helps to explain, or that might have to do with at least this sort of surprising finding of these different rates. Okay, so quickly summarizing this part, we've mapped out the four-stroke diagram of double-stranded RNA. We find that the bending and twisting resistance is very similar, stretch one is a little bit lower, but there are really two surprising differences in the twist stretching dynamics. Well, I was sort of out of time when I started speaking, but I have 2 more slides. Don't worry. So just to maybe give you a flavor of how these techniques now can be leveraged to do other things than just studying sort of a naked nucleic acid. Here's a quick story where we use these freely orbited tweezers where the DNA is pulled up but free to rotate, where we flushed in RAD51, which is a protein that involved in homologous recombinations, a DNA repair mechanism, and we were able to assemble filaments. And it turns out when RAD51 binds to the DNA, it goes lengthens the DNA and then unbinds it. What happens is the bead goes round and round and round like on a spiral staircase. You can quantify this both in extension and angle, and from this we were able to reduce essentially properties, in particular the helicity of the filament, but there was some sort of contradiction to the literature. Another quick story that I'd just like to really mention. Another same assay, we pull, bead is free to rotate. In this case, we don't put a filament, but we put individual nucleosomes. We use NAP1, which is a sort of a nucleosome chaperone to load them onto. While the nucleosome, and I assume you know there's at least essentially spools that the DNA is wrapped around, while they get basically inserted, both the length changes, that's pretty clear, right, because you spool a little bit of DNA around the nucleosome, but also actually the rotation angle changes. That was known these nucleosomes have a non-trivial topology, and we now see these changes both in Z and angle at the same time. We do this for nucleosomes, which have the H3 and H4, but also H2A, H2B, but we also do it for tetrasomes, which have only H3 and H4 dimensions. And it turns out the tetrasome assembly proceeds in steps, but the overall topology is the same. And then there was one surprising finding that I'd like to mention. We found that the nucleosomes, once they were assembled, they're pretty stable. They stay there essentially for hours. The tetrasomes showed some very interesting dynamics, and then we do the length, I don't show you that, the length didn't change, so they didn't come off or on, but we saw fluctuations in the topology, so there seemed to be a left-handed and a right-handed version essentially of these tetrasomes. It likes to be mostly left-handed, so it's been most of the time down, and occasionally off up here. And we have some speculations how that actually might help alleviate some of these torsional stresses during transcription and translation. Okay, with this I'd like to thank my lab, my collaborators, and you for your patience. Thanks.
One question in light of time.
Hi, I was wondering, in a physiological type situation, how much of an effect on the total potential do you think the twist stretch coupling would have?
Yeah, that's a great question. I mean, you would think it could definitely have an effect. Like, for example, let's say, imagine you have a deletion mutation, right? So you take out a base. So this will change actually affect both the length and the helicity of, say, 2 binding sites. So the twist stretch might very well play a role. To be totally honest, it's a relatively small parameter. You know, I mean, we needed very precise measurements to pin it down. So, I mean, presumably bending and twisting rigidities are actually the more important ones. Also, the stretch one, because while we can measure it, since it's fairly large, in the cell, the DNA probably, or RNA probably get fairly rarely stretched to that extent. But, yeah.
Thanks a lot.